This is where the approach changes. In the previous lessons, carbon dioxide was the fluid you stored and controlled. Now it becomes a tool. It does not dissolve the rock. It controls how the acid reacts with it. The usual mistake is to focus on strength. Stronger acid. Faster reaction. On the surface, that looks effective. But it is not. When the reaction is too fast, the acid is consumed near the wellbore. It never reaches deeper damage. So the problem is not strength. It is control. Increasing acid strength does not solve it. Controlling the reaction does. This is where carbon dioxide changes the system. It alters the reaction environment. It slows the reaction down. And that allows the acid to travel further before it reacts. That is the real advantage. You achieve deeper penetration, better distribution, and a more efficient treatment. The principle is simple. Controlling the reaction matters more than increasing its intensity. Final line. A controlled reaction delivers better results. The real problem in conventional acidizing is how the reaction is treated. It is usually based on one assumption. Stronger acid gives better results. That assumption does not hold. A strong acid reacts immediately. It is consumed near the wellbore and never reaches the deeper damage. The outcome is inefficient. You remove damage close to the well, but leave a significant portion untreated. Penetration remains shallow. Most of the acid is spent before it is useful. The objective needs to change. You are not trying to increase the reaction. You are trying to control it. That means extending penetration, managing reaction rate, improving distribution, and reducing corrosion risk. This requires a shift in approach. Do not increase acid strength. Control how the reaction behaves. This is where carbon dioxide becomes important. It is not the active acid. It controls when and where the reaction takes place. Two approaches can be used. In a carbonic acid system, carbon dioxide reacts with water to form a weak acid. The reaction is slower, and penetration is deeper. In a hybrid system, a stronger acid acts near the wellbore, while carbon dioxide moderates the reaction deeper in the formation. This allows effective cleanup near the well, and controlled penetration beyond it. The principle is straightforward. The acid dissolves the rock. Carbon dioxide governs the reaction. Final principle. Controlling the reaction is more effective than increasing its strength. The reason this works is not preference. It is chemistry. Start with the nature of the fluid. Carbonic acid is a weak acid, much weaker than hydrochloric acid. Because of that, it does not react immediately. It allows the fluid to move into the formation before the reaction begins. The reaction itself is also slower. Compared with hydrochloric acid, the reaction rate with carbonate rock is much lower. So the acid is not consumed near the wellbore. It travels deeper into the formation. This directly increases penetration. There is another important effect. The dissolution is less aggressive. It does not attack one point intensely. Instead, the reaction is spread out. More of the rock volume is treated, rather than forming a single dominant channel. This is how the mechanism works. The fluid moves forward, and the reaction progresses with it. The reaction front does not stay at the face. It moves deeper into the reservoir. Now compare the two systems. With carbon dioxide, the reaction is slow, penetration is extended, and dissolution is more uniform. With hydrochloric acid, the reaction is fast, the acid is consumed near the wellbore, and flow is focused into preferential paths. So the value is not in how aggressive the reaction is. It is in how well it is distributed. Final principle. Better distribution creates better performance, not stronger reaction. Now move from mechanism to design. A slower reaction gives you reach, but a weak system alone is not enough. You still need strength near the wellbore to remove severe damage. At the same time, you need control to reach deeper zones. That balance leads to a hybrid approach. Near the wellbore, a strong acid reacts quickly. It removes scale, deposits, and tightly bound damage. As the fluid moves deeper, carbon dioxide changes the reaction environment. The reaction slows down, and the remaining acid can travel further into the formation. This creates a clear outcome. You get strength where it is needed, and control where it matters. This is not about maximum strength. It is about controlled strength. The benefits follow naturally. Penetration increases. Less acid is wasted. Distribution improves. More of the formation is treated. Corrosion is reduced, and overall efficiency improves. There are limitations to consider. A weak system alone cannot remove severe damage. Carbon dioxide does not replace acidizing. It improves how it works. There is also an operating constraint. Carbon dioxide must remain in the correct phase. If pressure or temperature changes too much, the system becomes unstable. When that happens, reaction control is lost. So the role is clear. Carbon dioxide is not a strength tool. It is a control tool. Final principle. Use strength to remove damage, and control to reach deeper into the system. Every system has limits. This approach only works when those limits are respected. If control is lost, the treatment also fails. Start with pressure and phase behavior. Carbon dioxide must remain in the correct phase. If pressure drops, its behavior changes. Once that happens, reaction control is lost. The system becomes unpredictable. Penetration changes, and efficiency declines. Fluid handling is the next constraint. Carbon dioxide has to be mixed precisely with the acid. Too much, and the system becomes too weak. Too little, and the reaction becomes uncontrolled. The balance is critical. Compatibility also matters. The formation controls how the system responds. Different minerals react in different ways. If this is not evaluated properly, unwanted reactions can occur. So this is not a simple treatment. It is a controlled system that must be managed. The difference becomes clear when you compare approaches. Conventional acid reacts quickly. Penetration is shallow. Dissolution is aggressive, and corrosion is higher. A carbon dioxide enhanced system reacts more slowly. Penetration is deeper. Dissolution is controlled, and corrosion is reduced. The key difference is not the fluid. It is the objective. Conventional acid maximizes reaction. A carbon dioxide enhanced system controls it. This leads to a practical decision. If the problem is severe damage, a strong acid is required. If the challenge is limited penetration, a controlled system is more effective. Final principle: do not choose the strongest option. Choose the correct one. Now move into real application. Understanding the system is one thing. Applying it correctly is another. Consider a typical case. A carbonate reservoir with moderate permeability, where acid is not reaching all zones effectively. The solution is not to increase acid strength. It is to control how the reaction develops. Replacing conventional hydrochloric acid with a carbon dioxide enhanced system can change the outcome. Injection must be controlled. Pressure must remain stable. Carbon dioxide must stay in the correct phase. When this is done properly, the acid travels deeper, distribution improves, and more of the formation is treated. Performance increases because the treatment reaches the right places. The lesson is clear. Improving distribution drives performance, not increasing strength. Now consider the failure case. The same type of reservoir, but a different decision. A carbon dioxide-only system is used for severe damage. The fluid reaches the damaged zone, but it is too weak to remove it. As a result, the damage remains, permeability does not improve, and the treatment fails. This highlights a basic truth. Weak systems cannot solve strong problems. This leads to a simple decision logic. If the damage is severe, a strong acid is required. Carbon dioxide alone will not solve it. If penetration is limited, a controlled system becomes effective. If distribution is uneven, a hybrid approach provides balance. Throughout all cases, pressure must be monitored. If limits are approached, the rate must be reduced immediately. Final rule: use carbon dioxide when control matters more than strength. Final principle: match the tool to the problem. Reduce everything to what matters. Carbon dioxide does not replace acid. It controls how the acid works. A strong acid reacts quickly, and a fast reaction limits penetration. When the reaction is controlled, the fluid travels further, and the treatment reaches deeper zones. So the value is not in strength alone. Penetration matters more than intensity, and distribution matters more than how aggressive the reaction is. A hybrid approach provides that balance. You use strength near the wellbore, and control as the treatment moves deeper into the formation. But this only works under control. Pressure must remain stable. The fluid must stay in the correct phase. Mixing must be precise. If any of these are lost, the treatment becomes ineffective. There are also limits to what this system can do. A weak system cannot remove severe damage. Control cannot replace strength. So the decision must match the problem. Do not choose the strongest method. Choose the correct one. The mindset is simple. Better results do not come from doing more. They come from controlling how the system behaves. Final principle: performance depends on penetration and distribution, not on reaction intensity. Final line: control the reaction, and you control the result. Now step back and look at how this really works. You have seen three approaches: strong acid, controlled systems, and hybrid designs. But none of them matter if the thinking behind them is wrong. Most engineers follow the same pattern. They increase strength. They increase volume. They push the system harder. That gives a quick reaction, but the result is predictable. Penetration stays shallow. Distribution is poor. Efficiency remains low. A controlled approach looks different. Instead of increasing strength, the focus is on behavior. The reaction is slowed. Penetration is extended. Distribution improves. The difference becomes clear in practice. Two engineers can work on the same reservoir with the same tools. One applies more force. The other controls the system. One wastes the treatment. The other improves the reservoir. The difference is not knowledge. It is discipline. Final principle: acidizing does not improve by becoming stronger. It improves when the reaction is controlled. Final line: control the reaction, and you control the result. Step back and look at the full picture. You have seen three systems and three different challenges. Hydrogen is the hardest to contain. Carbon dioxide storage is limited by pressure. Carbon dioxide-enhanced acidizing is controlled by reaction. They look different, but they follow the same rule. Everything depends on control. Containment must be protected. Pressure must stay within limits. The reaction must be managed. None of these are improved by pushing harder. The common mistake is simple: trying to improve performance by doing more. More flow. More pressure. Stronger treatments. That approach always leads to the same outcome: loss of control. And eventually, system failure. The correct approach is different. You control the system. You control the pressure. You control the reaction. That is what delivers reliable results. Final principle: success does not come from doing more. It comes from controlling the outcome. Final line: control the system or lose it.